Hello there! In this lesson, we are going to talk about conservation of angular momentum. But before we go over to that, we need to understand the concept of angular momentum. Now, whenever an object rotates, something causes it to rotate, right? And it will eventually come to a stop. Something also causes it to stop as well, right? A tug exerted on a wheel causes its angular velocity to change, just as a force will cause the linear velocity of an object to change as well, right? Now, any rotating object that tends to continue to rotate is evidence that there is a momentum associated with its rotational motion. And we call this momentum angular momentum, L. Angular momentum, given as L. This angular momentum is the lookalike of linear momentum, and it plays a central role in our study of rotational dynamics. Its relationship to linear momentum P is exactly the same as the relationship of torque to force, which we know as tau equal R cross F, right? So we define angular momentum L as mathematically as L equal R cross P. Now this is also the relationship between angular momentum and linear momentum, just as like that of torque and force. Now the unit of angular momentum is given as units is in kilogram meter square per second. You know, units in physics are very essential, okay? If you recall, we said that V equal RW, right? And this shows the relation that the linear velocity has with the angular velocity. Let's rewrite this equation now. L equal R cross, P, which is the linear momentum, is given as mv. So when we put this here, we have R cross mv. Okay, so now this relation comes in. And if we put this into this equation, let's call this equation 1. So we stop using this equation, okay? So if we put that into equation 1, we'll be having R cross, wherever we see V, we put RW. So we have M over RW. So when you open up the bracket, you have R cross M RW, which equals M R square W. We can write that clearly as L equal M R square W. Now there is a term called moment of inertia. Now this moment of inertia mathematically is given as I equal M R square. If we're looking at an entire body about a point, it's defined as the sum of the product of the masses of the particles and the squares of their respective distance from the axis or points. Okay, so where we have moment of inertia to be this, if we impute it into our equation, let's call this equation 2. Okay, if we impute it into this equation 2, we get another relation, L equal I W, right? So that is that. In three-dimensional space, the position vector arrow locates a particle in the xy plane with linear momentum. What do I mean by this? Let's have our three-dimensional space. This is the y plane, the x plane. We have y, we have the z, and we have the x plane. So now we have the position vector. Okay, this is our point 0 here. we have the position vector r to be in this direction. This is r. Okay, because it's a vector, we indicate with an arrow showing its direction. Okay, then we have the angular momentum in this direction, L. And we have the linear momentum as well, moving in this direction. That's the linear momentum of the particle moving in this direction. So we have P. Okay, so we connect the dots. We have this, okay, connected to this with respect to the point O, and we have this. So P makes an angle theta, okay, in respect to the position vector. Now the angular momentum with respect to the origin is L equal R cross P, which we know already, and it is in the Z direction. The direction of L is given by the right hand rule, and its magnitude now is L equal mvr sine theta. You can look up the right hand rule at your own private time, okay? So we have the direction to be L equal mvr sine theta. Now, where we know, now other lessons where we talked about torque, we found out that small l equal r sine theta, where this L is the perpendicular distance from the line to the point 0. So if we put this back into this, we have L equal mvl. So now this distance plays the role of lever arm. L here plays the role of the lever arm, okay? That's how to find the direction of the angular momentum of a particle in a three-dimensional space. Okay, so just know that whenever it is mentioned that you're asked to look for the direction of the angular momentum of a particle, and probably the dimensions was stated, whether 2 dimensions or 3 dimensions. But for this case, it is 3 dimensions. Our direction is given in r sine theta, okay? Now when a net force F acts on a particle, its velocity and momentum change. So its angular momentum may also change as well. We can show that the rate of change of angular momentum is equal to the torque of the net force. So if we take the time derivative of angular momentum L, using the rule for the derivative of a product, we'll get the L now, taking the time derivative of angular momentum. Note that L equals mvr, right? So we're going to take the time derivative of r first. So when we do that, we have the r over the t cross mv. Put that in brackets. So we're taking the cross product now of this momentum. So we have that plus, so leave r. So we leave r and take the time derivative of v now. We have m dv over dt. Okay, so the r over the t is velocity, right? So we put that down, v cross mv plus r cross m The v over the t is acceleration, right? That's the change in velocity over time. So we put that down a. So we can have, so we have the L over the T. If we take the cross product of this, we have, of this first term, we have 0 plus R cross MA. Now the first term is 0 because it contains the vector product of the vector V with itself. So in the second term, so we can have this as the L over the T equal R cross MA. Okay, now this term here, we can replace with the net force F. So if we do that, we have the L over the T equal R cross F. Equal R cross F, and this equals torque. Now this means that the rate of change of angular momentum of a particle equals the torque of the net force acting on it. Now you can see how we've been able to connect the dots. We've been able to relate one quantity to another quantity. That's why it is essential you know the quantity you're dealing with, okay? Getting its formula or derivative would not be an issue. Now, angular momentum forms the basis for the principle of conservation of angular momentum, which we will take in a bit. So hang in there.